Why do I say this? Well, let me start with a story. During the war in the South Seas, there were these islands where cargo planes would land, bringing all sorts of wonderful materials. The natives saw this, and after the war ended, they wanted the cargo to come back. So they did something fascinating. They built runways. They put fires along the sides of the runways, just like they'd seen. They made a wooden hut for a man to sit in, with 2 wooden pieces on his head that looked like headphones. They put bars of bamboo sticking out like antennas. He's the controller. And they waited for the airplanes to land. They were doing everything right. The form was perfect. It looked exactly the way it looked before. But you know what? It doesn't work. No airplanes land. And this is what I call cargo cult science, because they're following all the apparent precepts and forms of scientific investigation, but they're missing something essential. The planes don't land. Now you're probably thinking, well, that's silly. Of course that wouldn't work. But here's the thing. We do this all the time, in our own lives, in our work, in what we call science. We go through the motions. We do everything that looks right, but we're missing something crucial. Let me give you an example from real science. You know about Millikan's oil drop experiment, right? He measured the charge on an electron by watching tiny oil drops fall in an electric field. Brilliant experiment. And he got an answer. But here's the interesting part. His answer was wrong, just a little bit off, because he had the incorrect value for the viscosity of air. Now, you'd think that the next person who did the experiment would immediately get a different number, right? Wrong. If you look at the history of measurements of the electron charge after Millikan, you find something peculiar. You find that one measurement is a little bit bigger than Millikan's, and the next one's a little bit bigger than that, and the next one's a little bit bigger than that, until finally they settle down to a number which is higher. Why didn't they discover the new number was higher right away? It's a thing that scientists are ashamed of, this history, because it's apparent that people did things like this. When they got a number that was too high above Millikan's, they thought something must be wrong. And they would look for and find a reason why something might be wrong. When they got a number closer to Millikan's value, they didn't look so hard. And so they eliminated the numbers that were too far off. They fooled themselves. They knew what the answer should be, and they made their results fit. Now, this is not fraud. These were honest scientists, but they were fooling themselves, because you see, you already have an idea in your head of what the right answer is, and when you get a result that doesn't match, you look harder for mistakes. When you get a result that does match, you don't look so hard. You're the easiest person to fool. Let me tell you another story. When I was at Cornell, I talked to people in the psychology department. One student told me she wanted to do an experiment. Other people had found that under certain circumstances, X rats did something A. She was curious whether if she changed the circumstances to Y, the rats would still do A. Sounds reasonable, right? She was very delighted with this idea and went to her professor. And his reply was, no, you cannot do that, because the experiment has already been done and you would be wasting time. Now think about that. You would be wasting time. Not trying to repeat the experiment, just changing the conditions and seeing what happens. This was the general policy then, not to try to repeat psychological experiments, but only to change the conditions. But here's the problem. How do you know the first experiment was right? How do you know what you're building on is solid? There was a man named Young who did a very interesting experiment in 1937. He had a long corridor with doors all along one side where the rats came in, and doors along the other side where the food was. He wanted to see if he could train the rats to go in at the third door down from wherever he started them off. No, he found they couldn't learn that. They could learn to go to the door with the food, sure, but the third door they couldn't seem to get it. So Young started investigating. Maybe he thought they're getting clues from somewhere. So he covered the corridor with a certain kind of smell. He thought the rats might smell where they'd been before. He tried to control for lighting so they weren't using shadows. But the rats still found their way. They still knew which door. Then he noticed something. He finally found that they could tell by the way the floor sounded when they ran over it. Can you imagine? The sound of the floor. So he could only fix that by putting his corridor in sand. He covered one clue after another, all the possible clues, and finally was able to fool the rats so that they actually had to learn to go in the third door. Now, from a scientific standpoint, that is an #1 experiment. That's the experiment that makes rat-running experiments sensible. because it uncovers the clues that the rat is really using, not what you think it's using. That's the experiment that tells exactly what conditions you have to use in order to be careful and control everything in an experiment with rat running. I looked up the subsequent history of this research. The next experiment and the one after that never referred to Mr. Young. They never used any of his criteria. They didn't put the corridor on sand. They weren't very careful. They just went right on running rats in the same old way and paid no attention to the great discoveries of Mr. Young. His papers are not referred to because he didn't discover anything about rats. He discovered all the things you have to do to discover something about rats. But people weren't interested in that. And that's cargo cult science. That's doing everything that looks like science. You've got the rats, you've got the maze, you've got the data, but you're missing something essential. So what's missing? What's the thing that makes real science work? It's a kind of scientific integrity, a principle of scientific thought that corresponds to a kind of utter honesty, a kind of leaning over backwards. For example, if you're doing an experiment, you should report everything that you think might make it invalid. Not only what you think is right about it, you should report other causes that could possibly explain your results, things you thought of that you've eliminated by some other experiment and how they worked, to make sure the other person can tell they have been eliminated. Details that could throw doubt on your interpretation must be given if you know them. You must do the best you can. If you know anything at all wrong or possibly wrong, you have to explain it. If you make a theory and advertise it or put it out, then you must also put down all the facts that disagree with it as well as those that agree with it. Now, I know what you're thinking. This sounds like it's going to make your work look bad, right? You're worried that if you point out all the problems, people won't believe your results. But here's the thing. This is exactly backwards. This is where the integrity comes in. The easiest way to explain this is to contrast it with advertising. You know those commercials that say Wesson oil doesn't soak through food? Well, that's true. It's not dishonest. But the thing I'm talking about is not just a matter of not being dishonest. It's a matter of scientific integrity, which is another level. The fact that should be added to that advertising statement is that no oils soak through food if operated at a certain temperature. If operated at another temperature, they all will, including Wesson oil. So it's the implication which has been conveyed, not the fact, which is true. In science, we can't do that. We can't just tell the part of the truth that makes us look good, because here's what happens. We've learned from experience that the truth will come out. Other experimenters will repeat your experiment and find out whether you were wrong or right. Nature's phenomena will agree or they'll disagree with your theory. And although you may gain some temporary fame and excitement, you will not gain a good reputation as a scientist if you haven't tried to be very careful in this kind of work. The first principle is that you must not fool yourself, and you are the easiest person to fool. So you have to be very careful about that. After you've not fooled yourself, it's easy not to fool other scientists. You just have to be honest in a conventional way after that. Now, I want to add something that's not essential to the science, but something I kind of believe. You should not fool the layman when you're talking as a scientist. I'm not trying to tell you what to do about your personal life. We'll leave those problems up to you. I'm talking about a specific extra type of integrity that you ought to have when acting as a scientist. Let me give you another example of how we fool ourselves. I meet lots of people who get me into conversations about UFOs or astrology or ESP or some form of mysticism, and I've concluded that it's not a scientific world out there. Most people believe so many wonderful things, so I decided to investigate why they did. And I got overwhelmed. There's so much junk. I went into isolation tanks. You know, they're dark and quiet, and you float in Epsom salts, and I got many hours of hallucinations. So I know something about mystical experiences from the inside. Then I went to Iselin, which is a hotbed of this kind of thought, and I kept finding more and more things that looked like science but weren't. Take the ESP experiments. People have been running these for years, and as various people have made criticisms as they've improved their techniques, the effects get smaller and smaller and smaller until they gradually disappear. All the parapsychologists are looking for some experiment that can be repeated, that you can do again and get the same effect, statistically even. They run 1 million people through tests, and they get a certain statistical effect. Next time they try it, they don't get it anymore. And then you find someone saying that it's an irrelevant demand to expect a repeatable experiment. Can you imagine? that it's somehow unfair to ask that we be able to do the same thing twice and get the same answer. This is cargo cult science at its finest. It looks like science. They've got statistics, they've got graphs, they've got papers, but the planes don't land. And here's what really bothers me. Ordinary people with common sense ideas are intimidated by this kind of thing. A teacher who has some good idea of how to teach her children to read is forced by the school system to do it some other way, or is even fooled by the school system into thinking that her method is not necessarily a good one. Or a parent, after disciplining their children in one way or another, feels guilty for the rest of their life because they didn't do the right thing, according to the experts. The experts who are doing cargo cult science, the experts whose experiments can't be repeated, the experts who are fooling themselves. So how do you avoid this? How do you never be fooled again? First, you have to understand that you want to be fooled. Your brain wants to see patterns even when they're not there. It wants to believe in the things you've already decided are true. It wants to ignore the evidence that contradicts what you think. You have to fight against this. You have to bend over backwards to try to prove yourself wrong. When you do an experiment and get a result, your first instinct should not be, great, I was right. Your first instinct should be, how might I be wrong? What could have caused this result other than what I think caused it? What didn't I control for? You have to be more critical of your own ideas than anyone else will be. You have to look for the ways you might be fooling yourself. Because remember, you're the easiest person to fool. Second, you have to be willing to report everything, not just the results that support your theory. All of them, the ones that don't fit, the weird outliers, the experiments that failed, everything. Because maybe that thing you threw out, that result you thought was just a mistake. Maybe that was telling you something important. Maybe you were wrong about what the right answer should be. Third, you have to be willing to say, I don't know. This is hard. People think that scientists are supposed to have all the answers. But the best scientists I know are the ones who are comfortable saying they don't know something. They're the ones who are still curious, still asking questions, still willing to be surprised. And fourth, and this is really important, you have to remember that understanding how to do science is more important than any particular result. Mr. Young didn't discover anything about rats, but he discovered something much more important. He discovered what you have to do to discover something about rats. That's the real contribution, not the answer, but the method. This long history of learning how not to fool ourselves, of having utter scientific integrity, is, I'm sorry to say, something that we haven't specifically included in any particular course that I know of. We just hope you've caught on by osmosis. But you can't count on osmosis. You have to actively work at it. You know, there's a certain danger of this cargo cult thinking, even creeping into physics now. I was shocked to hear of an experiment done at a big accelerator where a person used heavy hydrogen. To compare his results to what might happen with light hydrogen, he had to use data from someone else's experiment on light hydrogen, which was done on different apparatus. When asked why he didn't do both experiments on the same apparatus, he said it was because he couldn't get time on the machine. There's so little time and it's such expensive apparatus. To do the experiment with light hydrogen wouldn't give any new result. It would just confirm that the apparatus works the same for both. But that's exactly what you need to know. You need to know that your apparatus works the same way for different conditions. Otherwise, how do you know what you're measuring? This is the kind of integrity that's being destroyed by the pressure to get new results, to keep the money coming in, to publish papers. The experimenters there find it hard to complete their work as their scientific integrity demands. And this brings me to my last point. You have to have the freedom to maintain this kind of integrity. You have to be somewhere where you're not forced by the need to maintain your position in the organization or to get financial support, to lose your integrity. This is hard. I know it's hard, but it's necessary. Because here's the thing about fooling yourself. Once you start, it's very hard to stop. One little compromise leads to another. One result you don't report because it doesn't fit leads to another. One experiment you don't do because you know what the answer will be leads to another. And before you know it, you're building elaborate wooden control towers and wondering why the planes don't land. So let me sum this up. The first principle is that you must not fool yourself, and you are the easiest person to fool. You have to be very careful about that. You have to bend over backwards to try to prove yourself wrong. You have to report everything, even the things that make your work look bad. You have to be honest about what you don't know. And you have to understand that the method, learning how to do science right, is more important than any particular result. This is not easy. It requires a kind of courage, the courage to say, I might be wrong, the courage to report results that don't support your theory, the courage to admit that you don't know something, the courage to do the hard work of controlling for everything, even when it seems like you're just wasting time. But this is what separates real science from cargo cult science. This is what makes the planes land. This is what keeps you from fooling yourself. And the beautiful thing is, this doesn't just apply to science. It applies to everything in life. Every time you're trying to figure out if something is true, every time you're making a decision, every time you're trying to learn something new, the same principles apply. Don't fool yourself. Look for ways you might be wrong. Be honest about what you don't know. Pay attention to the evidence, all of it, not just the parts that support what you already believe. Because in the end, nature is the final judge. You can fool yourself, you can fool other people, but you can't fool nature. If your airplane is made of wood and bamboo, it won't fly, no matter how much it looks like the real thing. If your experiment isn't controlled properly, the results won't mean what you think they mean, no matter how much you want them to. The truth will come out eventually. So do yourself a favor. Don't wait for the truth to come out and prove you wrong. Go looking for the ways you might be wrong. Try to prove yourself wrong. Be the hardest critic of your own ideas. Bend over backwards to maintain your integrity. That's how you never get fooled again. Not by making yourself impossible to fool, that's not possible, but by constantly being on guard against fooling yourself, by making it a habit, a way of thinking, a kind of integrity that you carry with you in everything you do. And remember, you're the easiest person to fool, so be very, very careful.